Hi guys, I'm Mohammed Usman. Now we are going to see about clustered system in operating system as in-depth exploration. These are the contents: introduction to clustered systems, architecture of clustered systems, communication in clustered systems, resource management, fault tolerance in clustered systems, performance evaluation, security issues in clustered systems, case studies and applications. Introduction to clustered systems. Definition and overview. What is a clustered system? A clustered system is a set of interconnected computers that work together to improve performance and ensure redundancy, effectively functioning as a single system of users. Historical development. Clustered systems have evolved from early mainframe computing to modern distributed architectures rooted in advancements in hardware and networking technologies that enhance computing capabilities. Importance of clustered systems: reliability and availability. Clustered systems enhance reliability by providing failover capabilities, ensuring that the system remains operational even if one or more components fail, which significantly reduces downtime. Scalability considerations. Scalability in clustered system allows for the seamless addition of resources or nodes to handle increased loads, allowing organizations to grow their computing resources without major redesigns. Architecture of clustered systems. Types of clustered systems: load balancing clusters, high availability clusters, grid computing. Load balancing clusters distribute workloads across multiple nodes to optimize resource utilization, enhance performance, and prevent any single node from being overwhelmed. High availability clusters are designed to eliminate downtime through redundancy, ensuring that if one node fails, service can be quickly redirected to other operational nodes. Grid computing. Grid computing enables the pooling of resources from multiple locations, allowing for large-scale processing tasks to be handled efficiently by connecting the separate system over the internet. Key components: node structure, interconnection networks, clustered management software. The node structure consists of individual units in a cluster that can function independently or together with the components including CPU, memory, and storage dedicated to specific tasks. Interconnection networks facilitate communication between nodes in a cluster, utilizing technologies like Ethernet or InfiniBand to ensure high-speed data transfer and coordination. Cluster management software oversees the operation of clustered systems, providing tools for monitoring performance, managing resources, and automating failover process to maintain uptime. Communication in clustered systems. Communication protocols. Message passing interference (MPI). The message passing interference is a standardized and portable message passing systems designed to allow processors to communicate with one another in a distributed computing environment, enhancing parallel programming. RPC, remote procedure call. Remote procedure call enables a program to execute a procedure on a remote server as if it were a local call, simplifying communication in distributed systems by abstracting the underlying network complexity. Data consistency models. Strong consistency, eventual consistency. Strong consistency ensures that any read operation reflects the most recent write, guaranteeing that all clients have a consistent view of data, which is crucial for applications requiring high reliability. Eventual consistency is a model that allows data updates to propagate through the system eventually, meaning clients may see stable data temporarily but will eventually reach a consistent state suitable for system prioritizing availability. Resource management. Scheduling in clustered systems. Task scheduling algorithms. Task scheduling algorithms are crucial in clustered systems, determining how tasks are assigned to nodes to optimize resource utilization, response time, and throughput. Dynamic load balancing. Dynamic load balancing techniques redistribute workloads among nodes in real time, ensuring efficient processing and preventing any single node from becoming a bottleneck. Storage management. Distributed file systems enable data storage across multiple servers, ensuring redundancy, improved access speed, and fault tolerance in data management. Data replication techniques. Data replication techniques involve creating copies of data across different nodes to enhance data availability, reliability, and speed of data access in clustered environments. Fault tolerance in clustered systems. Failure detection methods. Health monitoring techniques. Terrain techniques involve regularly checking the status and resources usage of nodes in a cluster to detect failures promptly, thereby preventing the major system outage. Heartbeating mechanisms are protocols where nodes send periodic signals to indicate they are operational. A missed heartbeat indicates a potential failure, triggering recovery processes. Recovery strategies. Checkpointing. Checkpointing involves saving the state of system at regular intervals. In case of a failure, the system can restore from a last saved state. Minimizing data loss and downtime. Redundancy approaches. Redundancy approaches increases system reliability by duplicating critical components or tasks. If one component fails, other can take over, ensuring continuous severe service availability. Performance evaluation. Metrics for benchmarking. Throughput analysis measures the amount of data processed in a given time frame, accessing the capacity and efficiency of a system under various loads. Latency measurements evaluate this time delay between a request and its corresponding response, crucial for understanding user experience and system performance. Tools and frameworks. Benchmarking tools are software applications designed to test and compare the performance of different systems, allowing for performance metrics analysis and optimization. Performance profiting profiling utilities. Performance profiling utilities provide insights into usage and resource usage and execution time, helping developers identify bottlenecks and optimize the code for better efficiency. Security issues in clustered systems. Vulnerability assessment. Threat models analyze potential threats to clustered system, assessing the different types of attackers, their capabilities and possible attack vectors that could compromise system integrity. Security breaches refer to incidents where unauthorized access occurs, leading to data leakage, system damage and loss of trust. Understanding breach incidents helps develop preventive strategies. Security mechanism. Authentication ensures that users prove their identity, while authorization determines access rights to resources. Together, this mechanism enforce source access control in clustered environments. Data encryption techniques. Data encryption techniques protect sensitive information by converting it into an unreadable format, ensuring that even if intercepted, the data remains confidential and secure from unauthorized users. Case studies and applications. Real-world implementation. E-commerce platforms utilize clustered systems to manage large volumes of transactions, enhance website performance, and ensure high availability during peak shopping times. Scientific research projects harness clustered systems for processing large data sets, enabling complex simulations and collaborative research across global institutions for improved data analysis. Future trends in clustered system. Cloud computing integration. Integration with cloud computing allows clustered system to scale dynamically, providing on-demand resources, cost efficiency, and enhanced data accessibility for enterprise and developers. Edge computing opportunities. Edge computing presents opportunities for clustered system by facilitating real-time data processing closer to the resource, thus improving response times and reducing bandwidth use in IoT applications. Thank you.